All right. So this video is about link layer. Link layer will require many lectures, but we are going to provide a summary in this again about half an hour video. So the agenda is we will motivate the need for link layer, how the channels are shared. We have used, every one of us has used Wi-Fi. This runs over the shared channel, many users trying to access the same shared resource over the air. We will talk about the packet delivery on the link and spanning tree. How is it used in the link layer, local area networks? Then we'll talk about the learning in layer 2 switches. So first of all, what is the job of the link layer? The job of the link layer is to provide best effort packet transfer on a local link. Remember, we talked about the end-to-end delivery between two hosts on the internet, one in one continent, other in another continent. The packet delivery from source to the destination is concatenation of many links and routers in between. So on each of the link, I have to send a link layer packet so that link by link, you go from all the way from the source to the destination. Okay, so link layer's job is to provide the delivery from one node or host or network device, we use this interchangeably, to an adjacent host or adjacent node. And the definition of adjacent is that these two guys have an IP address which is in the same range, such that these two guys are considered to be on the same subnet, same network, same local area network. Okay, so you do not cross a layer 3 switch, which is a router boundary. If you cross a router boundary on one side of the router and on the other side of the router, you would have two different sort of local area networks. Everything on one side of the router, connected through one interface of the router, will be a single local area network, a single subnet. Okay, so crossing a layer 2 switch is okay, because layer 2 switch does not change your subnet. It just extends the definition of the link. You can stick in a layer 2 switch in between, one wire on the left, one wire on the right, and these two wires left and right, they are part of the same link. This is considered to be just a link which is extended. Okay, what are the services provided by the link layer? First of all, it needs to provide the link access and framing. It must encapsulate the IP datagram. Remember, the network layer, which is above the data link layer, will make the IP datagram, and inside the IP datagram, obviously there would be a TCP or UDP segment. So IP datagram needs to be transferred to the other end of the world, to some destination machine. This IP datagram is handed out by the network layer to the data link layer, and the job of the data link layer is to put that IP datagram in a frame, add a header and a trailer, possibly depending upon what kind of link layer we are using. And in the case of network layer, where we use the IP addresses for source and destination, in the case of link layer, we use the MAC addresses or hardware addresses or physical addresses, as we call them. These MAC addresses are used to identify the source and destination hosts, and they are very local on a single subnet, Okay. And also the link layer, the job of the link layer would be to provide the channel access if the medium is shared, as we talked about in the case of wireless. Some link layer services would also include reliable delivery between the adjacent node. You will definitely have the delivery of the frame or link layer packet between the adjacent nodes, but is that delivery reliable or not? It could be reliable in some cases and not necessarily in some other cases. We do know how to do the reliable delivery. We talked about the reliable data transfer in earlier lectures when we were talking about TCP. So the reliable delivery paradigm is not used in links which are low bit error rate links, because there is a cost of using reliability, cost of the overhead of providing reliability. We don't want to provide this overhead if 1 out of a billion bits is going to be in error. But if the errors are frequent, such as in the wireless case, the error rates are very high. 1 in 1,000 bits or 10,000 bits would be in error. In that case, we would be willing to pay the price of providing reliability and will provide reliable delivery between the adjacent nodes. Additional services of the link layer is to provide flow control. This is exactly the same flow control without overwhelming the receiver. You need to pace the sending rate between the adjacent sending and receiving nodes. Also provides error detection. Error could be caused by signal attenuation, random noise, etc., and in some cases error correction as well. And finally, it can also provide half duplex or full duplex kind of service. What does that mean? Full duplex means that two end hosts are talking to each other simultaneously. Half duplex means they can still talk to each other, but not simultaneously. A will be talking to B and then B will be talking to A, but not simultaneously. Full duplex means they simultaneously are able to talk to each other. Okay. So where is the link layer implemented? Link layer is implemented in each and every host which is equipped with a network interface card. So every PC, even your phone, will have a Wi-Fi network interface card. So the link layer is implemented in the network interface card adapter, which could be a Wi-Fi 802.11 type of an interface card, an Ethernet card, or some maybe built-in kind of an interface card using the Ethernet standard. So this implements the link layer as well as the physical layer. The network interface card typically will implement both of these layers, and this is attached to the host system buses through PCI slots, or maybe integrated into the motherboard. Okay, this is a combination of hardware, software, firmware. You might have a combination of these to provide the link layer functionality. So if you look at the link layer, you would have these interfaces communicating over a single link. These two interfaces are adjacent to each other on the left and right. If the network layer on the left guy wants to send an IP datagram from the network layer to the network layer on the right hand side, this datagram is handed over to the link layer, and the link layer will encapsulate the datagram in a frame and do the other services that we already talked about, and will send this datagram onto the other side, where including the link layer header, where the datagram will be extracted out by removing the link layer header, and this datagram will be handed over to the network layer. And this is the job of the link layer, to service the network layer. So network layer will be getting the services from the link layer, which is underneath. So now let's take a look at the types of the data links. We can have point-to-point links. For example, you can have a layer 2 switch here, layer 2 switch, an Ethernet layer 2 switch, and then 6 hosts are connected to 6 different physical interfaces by means of these Ethernet cables. So this is 6 point-to-point links between the Ethernet and the 6 end devices. In fact, if you connect two devices, two computers directly with each other by using the Ethernet cable, that is also going to be a point-to-point link. In this case, you have 6 point-to-point links. You can also have point-to-point links for dial-up access. Dial-up access is not used anymore. Well, maybe it is still used anymore, but not very prevalent. Has been replaced by cable and other kind of fiber to the home kind of services. In addition to the point-to-point links, there is another type of data links, which are broadcast links. Broadcast links means shared wire link or wireless links, and there are multiple examples of that. You can have an old-fashioned Ethernet kind of a link, a single piece of wire running here and machines connected on that single piece of wire, which means if one machine will transmit something, everyone will listen to that. Okay. This does not happen in the case of point-to-point links. Similarly, 802.11 wireless link, if I transmit, everyone in the vicinity will be able to listen to those packets. Maybe they will not be able to make any sense out of those packets, but they will still be able to listen to those packets. And similarly, the satellite links are also shared links. They are using this shared network resource. Okay. So what is this broadcast transmission channel? Broadcast transmission channel, when any one node transmits a frame data link layer packet, multiple nodes can receive a copy of that. So two or more simultaneous transmissions by node will cause an interference, a collision of the packets and an interference. If you have a shared channel and multiple people transmit, their packets might collide with each other and interfere with each other, which means that they will be garbled. If you are transmitting packets as electromagnetic waves, these electromagnetic waves are transmitted, and a packet is just a sequence of bits. My bits and your bits might get collided with each other, which means the signals will be garbled. They will be added together either constructively or destructively, and you will get nothing. And nobody will be able to receive those. Well, they will receive those, but it would just be garbage. So how do we avoid the interference and collisions? Maybe we use some sort of a multiple access protocol. This is like the same thing that, multiple people in the room, if they simultaneously try to talk, multiple conversations, nobody will be able to discern what is happening. But if people take turns, I talk first and you talk next, or you talk first and I talk next, then taking turns, this is an example of a multiple access protocol. You can avoid interference and collisions that way. So the human analogy is that if one person is talking and you start talking too, most likely no one will be able to understand. So to address this humans at a party kind of a situation, we use some sort of a protocol. So conversation manners, basic conversation manners will tell us that a very simple protocol of doing that is that you don't interrupt others. If somebody else is talking, if you observe someone is talking, you wait for them to finish. And once they are finished, then you start talking. Once you will be talking, and hopefully other people will be implementing the same protocol, and things will work out fine. Okay. So what is an ideal multiple access protocol? Moving on from the human analogy, we are talking about the network interface cards who need to transmit packets, and we don't want multiple guys to be transmitting packets simultaneously. Okay. What is a multiple access protocol ideally? So you are given a shared network resource, a broadcast channel whose rate is R bits per second. You can transmit, let's say, 100 megabits per second. Okay, 100 megabits per second. You cannot transmit faster than that with all the users combined. Okay, but multiple guys cannot transmit simultaneously. They must take turns or do something else. Okay, the desired properties at the highest level, the desired property from an ideal multiple access protocol is that when one node wants to transmit, if there is only one guy who wants to transmit, it should be able to take the entire bandwidth, entire broadcast channel rate. It should be able to send at a rate of R. Okay. If there are multiple guys who want to transmit, if two guys want to transmit, they should be able to transmit at R by 2, R by 2. Three guys should be R by 3, R by 3. And if M nodes want to transmit, each one can send at an average rate of R by M. Okay, R by M. So we want to be fair. We want everyone to be able to transmit. We want to be fair to them. So what the second point is dictating is that there is a fairness here. Okay, also dictating that the total rate still does not exceed R. The sum of the rates of individual nodes will not exceed R. We also want this scheme, this ideal multiple access protocol, to be fully decentralized. I don't want some guy sitting in the network and doing dictations that now you transmit, now you transmit, now you transmit. Okay, so I want this to be done, accomplished in a fully decentralized way. No synchronization, no coordination. It has to be simple. It has to be simple. Whenever I have packet, I should be able to transmit. Maybe after some delay. Maybe similar to humans in a party. Many people want to talk, so I will wait until somebody else finishes. So in order to accomplish this, I need a what we call a multiple access protocol, or media access control, or MAC protocol, media access control protocol. Okay. There are many MAC protocols or multiple access protocols which exist. We are not going to talk about all of those. Just will give you a brief high level view of the broad classes. which are used to share the access the shared medium. One is channel partitioning protocol, in which you have time slots or frequencies divided. So I transmit at one frequency, you transmit at another frequency. This is similar to what happens when multiple radio stations in a region are transmitting simultaneously. They do not interfere with each other because they are transmitting at different frequencies. I can receive whatever frequency I want to receive. I want to receive FM 100. I will just tune my radio receiver to 100 megahertz, and I will receive FM 100. If I tune it to 110 megahertz, I will receive FM 110. Okay, so you allocate a piece of resource to each of the transmitter. Okay, instead of frequency, we can also have time slots. So I take 1 second to transmit, and then you take 1 second, and somebody else takes 1 second. So this is dividing the channel into these smaller pieces, and pieces could be time slots, frequencies, or codes. Okay, we can also have random access. In this case, channels are not divided, but in this case, we allow collisions. People can transmit simultaneously. However, we do know that collisions are bad. When the packets collide, nobody is able to receive those because the energy is garbled. The electromagnetic signals, they are interfering with each other. Nobody is able to receive them correctly. So you recover from collisions. You allow collisions, but you recover from collisions. Okay. In this case, whenever you have a packet, you will be able to transmit that. Or you can also have a taking turns type of protocol. So in this case, what you would like to do is maybe, like a token ring kind of a protocol. In a ring, there is a token circling around. Whoever has that token will be able to transmit. Other might not be able to transmit. Okay. We are only going to talk about the random access protocols, channel partitioning, taking turns protocols. We will escape those. Okay. So in the case of random access protocols, whenever a node or a station or a host has something to send, you transmit at the full channel rate. If there is a 100 megabit per second channel available to you, you just transmitted that. You know that it is shared with the others as well, but whenever you have data to send, you just transmit. There is no a priori coordination, no coordination between the nodes when who will be transmitting. Whenever you have something to transmit, you just transmit that. So if 2 or more nodes are transmitting at the same time, this will lead to collision. Obviously, this will lead to collision, and random access MAC protocol specifies how to detect the collisions and how to recover from those collisions. And some of the examples of these protocols are carrier sense multiple access protocol, carrier sense multiple access CSMA protocol with CD collision detection, or CSMA protocol with collision avoidance. Aloha is one of the older protocols which used to be used. We don't use it anymore. So let's just talk about the CSMA protocol, which is one of the most popular one. The key idea behind the CSMA protocol is you listen before you transmit. If the channel is busy, if somebody else is transmitting, you will be able to sense it. You defer your transmission. This is the human analogy of not interrupting others. If somebody else is talking, you do not talk, you wait for them to finish, and then you transmit. Will this avoid collisions? Maybe yes, it looks like it might be able to avoid collisions, but what happens if there are 2 people at the far end of the room, and it will take some time for the audio to travel from one end to the other end, and the other guy also starts talking. So this may avoid collision in most of the cases, but collision may still occur. And why is that? Because there is a propagation delay, which means that 2 nodes which are far apart, they may not be able to hear each other right away. They are at far end and they will transmit simultaneously. And the chances of collision in this case obviously is dependent upon the distance and propagation delay. But there is a chance that signals will collide, packets will collide. So what happens when there is a collision? If there is a collision, the entire packet transmission is wasted. The entire packet transmission is wasted. So the whole packet, maybe it took you a few milliseconds to transmit that packet. That time is wasted. You will have to retransmit that packet. So this is the basic carrier sense multiple access. An enhancement to the carrier sense multiple access is a carrier sense multiple access with the collision detection. As soon as you detect the collision, you stop transmitting. Even if your transmission is not finished, you have transmitted maybe 5% of the packet bits, you just abort, you just quit at that time transmitting that packet. Okay, so CSMACD is carrier sensing, and you sense whether somebody is transmitting. If somebody is not transmitting, you can transmit, but if somebody is transmitting, you defer, as you do in the case of the plain CSMA. If the collisions are detected, they will be detected in a very short period of time. What that means is, when colliding transmissions are detected, you will abort those, you will reduce the channel wastage. So for example, you started transmitting, and when you started transmitting, obviously at that time nobody else will be transmitting, otherwise you would have deferred the transmission. So you only transmit when you do not hear anyone else transmitting. But it is possible that when you start the transmission, soon after you start the transmission, you will hear that somebody else is also transmitting. At that time, what should you do? Should you continue with your packet? No, you should stop. In the case of CSMA, you will continue with your packet and finish the transmission of the packet. But in the case of CSMA CD, you will abort. So this is the human analogy of a polite conversationalist. So if I start talking and you start talking, if there is a simultaneous kind of a thing, I will immediately stop if I hear that you are talking, even if I have started. Okay, so a collision will still be happening. The collision detection can be done in both cases, wired LANs as well as the wireless case. In the case of wired LANs, it is easy to detect the collision. So what you do is that when you are transmitting, at the same time your receiver is also receiving. So you compare the transmitted signal and the received signal, and you measure the signal strengths. And the difference between these signal strengths will tell you whether you are transmitting at the same time when somebody else is transmitting, or when you are receiving something. In the case of wireless LANs, it is difficult to detect when the collision happens. So that's why we do not use CSMACD in the case of wireless protocols. In the case of wireless, for Wi-Fi, we use what we call CSMACA, which is carrier sense multiple access with collision avoidance. The reason that we are unable to do collisions easily in the case of wireless is because the received signal strength is very, very small, overwhelmed by the local transmission. And the reason for that is, on a wireless medium, the signal strength, so signal energy, falls very sharply with the distance. Okay, so you might be transmitting a very high powered signal, but you will be receiving a signal which would have a very, very low power. Although when it was transmitted by somebody else, it had a high power at their node. But when it reached you, the signal strength has decreased quite a bit, so low that you are unable to even detect it. Okay? So the Ethernet CSMA CD algorithm, which is used on almost prevalent in all the Ethernets, is that your network interface card, it will receive an IP datagram from the network layer, will create a frame. If the network interface card senses that the channel is idle, you will start the transmission. If you sense that the channel is busy, then what you will do is that you will need to wait. You will wait, and once the channel is idle, you will transmit. So if you are able to transmit the entire frame, and during that time you did not hear anybody else talking, you will be satisfied that you have completed your job. You have transmitted your frame. Your packet is done. You are done with that. Is that the case? Well, it is the case if your frame meets a certain requirement. I'm not going to go into the details of that. Your frame has to be of a minimum size in order to be satisfied that once you are able to transmit the entire frame, is it really the job is done, or could there still be a collision? If the frame meets that minimum size criteria, then you will be guaranteed that there will be no collision. Okay. If the network interface card detects another transmission while you are transmitting, it will abort and send a jam signal as well. And after you abort, you will need to retransmit that frame. But you do not retransmit that frame immediately, because if everyone does that, then the likelihood that it will be a collision again is very, very high. So what happens is that you need to wait, and you need to wait for a random amount of time. So three guys whose signals collide with each other, all three of them will wait, but they will not wait for an equal amount of time. They will be waiting for a random amount of time, so that the chances of collision are minimized. How much time do you need to wait? You will need to generate a random number. If there are more collisions, then probably you would need to generate a random number which is large. You will need to wait for a longer time, still random, but longer time. So after the mth collision, you will choose a value k from this set 0, 1, 2, 2 to the power m minus 1, and you will wait k times 512 bit times and will return to step 2. Okay, will return to step 2 where you are ready to transmit. Okay, so you will need to wait certain amount of time, and that time is randomly collected, randomly randomly picked between 0 and 2 power m minus 1 multiplied by 512 bit times. So which means that if you have more collisions, then there will be longer back off interval with each of the collision. Now let me just move to local area networks and addressing. We have seen this kind of a figure before. On the left and on the right, we have hosts with all the 5 layers of the networking stack built in. We have a router which is shown here, which has the physical and link layer, obviously, and also a network layer, because the router is part of the IP network. We also are showing a layer 2 switch, which only has the physical and the data link layer, but it does not have the network layer. And the reason for that is the link on the left side of this layer 2 switch and on the right side of this layer 2 switch, it's the same link. It is considered to be the same link or part of the same link. This is an extended link on left and right of this layer 2 switch. On the other hand, this router has one link layer protocol running on the left side and a different link layer protocol running on the right hand side, 2 different subnets in this case. Okay. So what is MAC addressing? Just like IP addresses are 32-bit long, we have these MAC addresses which are 48 bits long, 48-bit long. Every network interface card will have an IP address to be present on the internet. Will also have a 48-bit MAC address or hardware address or physical address, which is shown here. Okay. Now you will notice here that in the figure we are showing a router, layer 3 switch, which is a router which is connecting this network to the rest of the outside world. We are also showing a layer 2 switch. Here, which is just extending these links with each other. So all these 4 links on which are connected with the layer 2 switch, they are part of this one giant link, if you like. Okay, so all the IP addresses shown in this network are on the same subnet or on a single LAN. Okay, specifically note this IP address which belongs to this left side interface of the router, which is 222.222.221, which is part of the same subnet. Obviously, this router will have other interfaces, and those interfaces will have different IP address which will not be the part of the same subnet. Okay. So how do we deliver the LAN frame on a local area network? Single link. How does the delivery of the frame on a single link work? Sender host machine will know the destination IP address. How does it know the destination IP address? Probably it knows the name of the machine and use the DNS resolution to get the IP address, or some other way of getting the IP address of the destination machine. It decides if the outgoing frame is a local LAN delivery or is a outside my LAN delivery or a different subnet delivery on another network delivery. Okay, there can be only these 2 possibilities. Okay, if it is on another network delivery, or as you call it, wide area network delivery, WAN delivery, then what it will do is that it will encapsulate the IP datagram into link layer frame and send the frame to the MAC address of the default router. It still needs to make a link layer frame, but instead of sending it to the destination, because the destination is not on my local area network, it is somewhere else, somewhere outside in the outside world, I will just make use of my default router. I still need to send the frame to the default router, and the default router is connected to me. on the same local area network, this router is connected, one interface of the router is connected to me. So I will send this to the default router. If it is a LAN delivery, if the sender host machine decided that it is a LAN delivery, which means the destination is on the same subnet on my local area network, then it will encapsulate the IP datagram into the link layer frame, just as before. And instead of sending to the router, it now has access to the destination. It will send it to the MAC address of the destination. Okay. Now, there are many unanswered questions here. Some of the questions could be, how does this host machine decide whether it is a LAN delivery or outside my LAN delivery, other subnet delivery? How would you decide that? Another questions could be, how do you encapsulate the IP datagrams into the link layer frame? What should be the destination MAC address on the link layer frame? How do you get that destination MAC address? Okay, and also, how do you send the frame to the MAC address of the default router? What is the mechanism of delivery? Is this something which uses the CSMACD kind of a link access protocol? So some of these questions could be these are the points that we need to think about. Given that the sender knows the destination IP address, how do you determine if it is a LAN delivery or a WAN delivery? On your network or outside your network? In this case, you compare your IP address with the destination IP address. Compare the subnet address of itself with the destination. In this case, you can make use of the subnet mask, which is available in your network configuration. If the significant bits in the subnet mask, which is the ones followed by zeros, if the number of ones there, so many bits of the destination IP address are exactly the same as your so many bits in your own address, that means the destination is on the same local area network. Otherwise, it is on a wide area network outside your local area network. How do you find the MAC address of the destination? Okay. Either the router, if you are sending it to the router for delivery to the WAN, or to a destination which is on your LAN. How do you find their MAC addresses? Well, you only know their IP addresses. If you know their IP addresses, you can use what we call the address resolution protocol to find the MAC addresses. This is the address resolution protocol is a translation mechanism from IP addresses to the MAC addresses. So how does the sender direct the frame to the destination? What is the mode of delivery? Maybe there is some multiple access protocol over the broadcast channel. The frame is sent to everyone. I will just transmit the packet and everyone in my local area network will receive that frame. And the hope is that the desired destination, whether it was the router who was helping me deliver the packet to the WAN or the destination on my LAN, whoever is the true destination, hopefully they will keep the packet for their own processing, and others will not keep it. But what is given is that if it is a broadcast channel and there are 20 hosts connected to that broadcast channel or on that broadcast channel, if I transmit something, everyone else will listen to that. And when everyone else listens to that, only one is the intended guy. They will keep it. Rest of the people will just drop it. Okay. But there are many bigger questions. How do you deliver it to these 20 guys? Okay. So how do you make sure that there is a frame delivery on the LAN? First of all, we need to ensure that the loops must not exist. We talked about loops not existing in the internet protocol delivery as well. But it is even more important in the case of local area network that there should be no loops or must be avoided. Why is that? Because otherwise the packets will proliferate. It is possible that I have one host connected to a layer 2 switch, another host connected to a layer 2 switch, and these two hosts are directly connected to each other. There is a loop right there. So you need to avoid the loop. How do you avoid the loop? Maybe in the single local area network topology, you find what we call a spanning tree. So you have one single subnet, single local area network, maybe a few layer 2 switches in there and many hosts in there. You find a spanning tree. And spanning tree is the one which touches upon all the hosts without any loops. So you will ignore the links that are not part of the spanning tree. So spanning tree by definition will not have any of the loops. And the result is that there will be only one path from any source to any destination which are on that spanning tree. This is not the optimal solution, but it will be working. Going from one source to a destination, there could have been multiple paths, a shorter path as well, but we will live with the longer path as long as we are able to avoid the loops. And how do you find that spanning tree? Well, we have an algorithm specifically for that. This was invented by Radio Pullman. This is called a spanning tree protocol, and the spanning tree algorithm, corresponding spanning tree algorithm. There's a protocol which exchanges information between the layer 2 switches, which form this spanning tree by using the protocol information. And this spanning tree can be found rather quickly. Okay. So how to route on the spanning tree? Once you have the spanning tree, how do you send the packet from the source to the destination on the spanning tree? And remember, we are still talking about one single link. This is a very giant link. All of these machines are on the same link. All of these machines are on part of the same subnet. So once you have the spanning tree on this big giant link, there is only one path from the source to the destination. How do you find that path? How do you find that path? Well, maybe it is not even important to find that path. Why bother? Just broadcast. Just send one packet and it will go everywhere on that tree. Everywhere on that tree. You are guaranteed that there will be no loops, because by definition the tree would not have any loop. Okay, so just send the packet along all the path and just broadcast it. So packet will not loop, and you will be dead sure that it will reach the destination, and exactly one copy will reach the destination. Obviously, there will be multiple copies made, but most of those copies will hit that end. There is definitely no question that you will have a loop in here. Okay. So how do you flood on the spanning tree? If you want to send a packet that will reach all the nodes, then switches and senders can use the following rules. That first of all, you ignore all the ports which are not part of the spanning tree, which means now you have stick to a topology. You have stick to a topology which has zero loops, which has no loops. If you just stick to the spanning tree. Okay. And the original node must broadcast the packet, by using maybe some sort of a multiple access protocol, CSMA, CD, let's say. Okay. And the frames arriving on an incoming interface of a layer 2 switch. Okay. If a layer 2 switch receives a frame on an incoming interface, it will be able to broadcast it out of all of the interfaces, if you do not know any better. No. So a layer 2 switch, if it receives a frame, it will just broadcast it everywhere. It is part of the spanning tree. It will just broadcast it anywhere without having any fear of the packet being in a situation that it will go into the loop. Okay. So so the layer 2 switch will just broadcast it on all the interfaces. Will it broadcast always? Well, if it doesn't know anything else, anything better, how to reach the correct destination, then it will just broadcast. And the question is, can you know anything better? I mean, flooding is wasteful anyway. Flooding is wasteful anyway. It ensures that the packet will reach the destination, but it is going to other places where it was not needed. Okay. Can you do something better? Can you avoid the flooding? Can you avoid the flooding? So layer 2 switches can avoid the flooding by means of what we call a learning process. They can learn where the different hosts are. They can learn where the hosts are. So a switch can learn how to reach a host by remembering where the packets came from. So if there is a host who is sending the packet, somebody will know that this guy who is sending the packet from the east, this guy is sitting on the east. Okay. So if a packet from host A enters a switch from interface 4, then the switch immediately declares that host A is accessible through that interface and no other interface. The reason that A is accessible from that interface is because the packet from A came through that interface. The reason that A is not accessible from any other interface is because we do not have any loops. We have a spanning tree working here. Okay, so you will store this information in a table which we call a switch table. It's much like a routing table. But it's called a switch table. It's only for layer 2 switches. So in the future, the switch, when it receives a packet which is destined for A, it will only send it to interface number 4 instead of flooding. So that's how you would avoid flooding. I have an example for that as well. So So layer 2 switch learning process, there is a single path between any two hosts. A switch can watch the packets going by and learn from that, can only watch the packets, which touches any of the interface or pass through the switch. A switch will not be able to see a packet which doesn't even touches it's any of its interfaces. So let's say, for example, a switch sees a packet going from host B to host C. Okay, the source was B and the destination was C. The B and C destination MAC address and the source MAC address, both of those are written within the packet. What can it include? Does the switch know? Does the layer 2 switch know? Does it know how to reach C? Does it know how to reach B? Well, the packet was from host B to host C. There is no way to find out where is host C, but I can probably tell. I will definitely be able to tell where is host B because host B has sent that packet. Okay. So what is written in the packet? The source and destination MAC addresses of B and C. Okay. So the switch knows which interface the packet from B came through. It was going to C. I don't know where C is, but I do know that it reached me through some interface. So I do know that this is the interface to reach B. This is the interface to reach B. It will declare to itself for future use and store it in the table, store it in the switch table that B is accessible via this interface. Okay. So one example of learning and avoiding the flooding. So this figure is showing a layer 2 switch with 6 hosts A, B, C, D, E, F connected to this. How does the switch know that D is accessible through interface number 4? How does this switch learn that F is accessible via interface number 6? Without D and F transmitting anything, the switch will not be able to find this out. But the hope is that D will transmit something, and then the switch will say, aha, D is connected to interface number 4. Okay, so the switch will maintain a switch table, and each entry in the switch table will have this MAC address or the destination MAC address of the interface of the host, and which interface this MAC address is accessible through, and there is a timestamp. After the timestamp is over, this entry will be deleted so that you can have a fresh entry. This is to accommodate when one host moves from one interface to another interface. So for example, in this case, B is connected to interface number 2 of the switch. What if somebody disconnects B and connects to interface number 17 of the same switch? So I need to make sure that we have some timed entries. There is some sort of a timeout with the entries. I should only keep the entries only for so long. Okay. So this looks like a routing table to me. So how are the entries created and maintained in this switch table? Okay. How do you create the entries? So in order to create these entries, you consider that when somebody is willing to send a frame. So let's say this frame is sent by station A or host A to host D. So the addresses of A and D, the MAC addresses of A and D are written within the frame, and then there is a rest of the stuff in here. Rest of the fields, the IP datagram in here, TCP port numbers, everything. The whole the packet will be sent. Rest assured, it would have the source and destination MAC address. When someone sends this kind of a frame, and this frame comes to the switch will look at the frame and learns the location of the sender. It knows that A has sent this frame, which interface A is connected to. Okay, so it will record the entry in the table. It will put the MAC address of the A here and the interface through which A is accessible here, and the time to live or the time after which this entry will not be valid, once again to accommodate any movement of station A or host A from this interface to any other interface. Okay. So how does this avoid flooding? I have made entries into the table. How is the flooding avoided? Well, the flooding is avoided because now when someone sends a frame to A, then this switch exactly knows that A is accessible through interface number 1. It will only send the frame on interface number 1 if it is destined for A. Otherwise, if it doesn't know where A is, it will have to broadcast. It will have to broadcast. Okay, so let's take a look at this example as well. How is flooding avoided? Okay, so when someone sends a frame, let's say A is trying to send a frame to D, and initially the switch will see the frame. There is no entry in the switch table, and once the switch sees this frame, the destination location is not known. The destination is D, doesn't know where D is. It doesn't know where D is. The switch table is empty. What it needs to do is it will just broadcast that. It will flood the frame on all the outgoing interfaces without knowing D. That's the best thing it can do. That's the best thing it can do without knowing the location of D. How is D accessible? So it will flood, but at the same time, it must make an entry in the switch table that now it knows that A is accessible through interface number 1. A is accessible through interface number 1. Later, D sends a packet response back to A, for example. So now the source is D and the destination is A. So later the switch will see this frame. Now the destination location is known. If the destination location is known, then it will just send selectively to A without flooding others. So this is how you will avoid flooding. You will still make an entry into the table because the source of this frame was D. Now the switch also knows that D is accessible through interface number 4, and this entry will go into the switch table as well. Okay. Now you can also have interconnected layer 2 switches, and learning can happen with interconnected switches. So we know the learning process on a single switch. What if you have multiple switches which are connected together, as shown in the figure, as shown in this figure? Okay, so if the switches are connected together, there is no issue with that. We can still do the learning. The switches typically will be connected to each other to make a bigger LAN. In this figure, all the stations, all the hosts are on a single subnet. This makes one single LAN. This is one big giant link per se. Okay, so let's say you want to send a frame from A to G. So source is A, the destination is G. A will make a frame, put the source address as A, destination address as G. How does this switch S1 know to forward this frame via S4 and S3 and not to S2? Well, it would not know. It would not know. It would just broadcast. Without knowing the location of G, everyone will just broadcast. All the switches will just broadcast. So in this case, the self-learning will happen because the switches are transparent. Nobody knows about the presence of the switches. The switches do not know the presence of other switches. The hosts do not know about the presence of switches. They just behave as if they are the only one on this local area network. So learning will work in exactly the same way as in the single switch case. So we have this example. Consider this local area network in which we have two links marked K1 and K2, link K1 and link K2. So let's say, first of all, host C, which is here, sends a frame 1 to host H. C is sending a frame to H. Okay. Host H will respond with frame 2. Host H will respond with frame 2. So two frames are sent, frame 1 from C to H and frame 2 from H to C, H back to C. So after the first frame is sent, but before sending the frame 2, okay, when C sends a frame, this switch S1 will receive it and it will broadcast it. It will be sent to A, it will be sent to B, because S1 doesn't know where is the destination. Where is the destination? It will be sent on K1. It will also be sent on K2. It will also be sent to D, E, F. It will also be sent by S4 to S3, and S3 will send it to G and H and I. Everyone has received it because none of the switches knew where is any of these destinations. To begin with, all the tables were empty. Then that means that the first frame which C sent, frame 1, has been broadcasted throughout the network. Everyone has received that. G will keep it. Everyone else will drop it. They will match the destination MAC address with their own MAC address. G will do the same thing. It will say, that destination is mine. So it will keep it. The others will say, the destination is not ours. So we'll just drop it. Okay. So how many frames were sent on link K1 and link K2 in this case? Just one frame was sent on link K1. Just one frame was sent on link K2. Okay. Well, when the frame which was sent on link K2, obviously it got replicated by the switch S2 to be sent on this link connecting to D, link connecting to E, and link connecting to F. Okay. But on the link K2, there was only one frame sent. Okay. Now everyone knows. Now everyone knows the location of C. Now everyone knows the location of C. G wants to respond back to C. What will happen in that case? Well, you might be able to fill in the switch tables for all the switches. Now they know the location of C. Now they know the location of C. So switch tables for each of these 4 switches, layer 2 switches, you should be able to fill those up. So when frame 2 is sent now, after the first frame, after frame 1, what happens now? Now G sends the frame, it will be sent to S3. Will S3 send it to H? No. To I? No. It will send it to S4 because S3 knows that C is accessible through this link, which is going towards S4. Will S4 send the frame to K2? It will not send the frame to K2. Why? Because now S4 knows, its table is telling it that host C is accessible through link K1. So there is no need to send the frame 2 on K2. Okay. So how many additional packets were sent on link K1? Again, just one. On K2, none. You will not send, S4 will not send any packet on link K2. Okay. So you can again update the switch tables. Obviously, when H has responded back to C, then the location of H is also now visible to some switches. Well, the location of H is visible to S3 and S4 and S1, but it did not become visible to S2. Why? Because the packet was not forwarded by S4 on link K2. So there was no opportunity for the switch S2 to learn about the location of H. Okay. So this quick summary of LAN delivery. LAN delivery avoids loop by restricting the transmissions to the spanning tree. This makes flooding possible. You will be able to do flooding. However, you try to avoid the flooding by making use of the learning process. So flooding allows a packet to reach the destination, and only one copy will reach the destination. And in this process, switches will learn the location of the flooding source. There is no explicit sort of route computation per se, but you will be able to send the packets to the destination. And the flooding will be avoided by using the learning process. Okay. So this kind of an approach of learning and layer 2 switches sticking together, this kind of an approach is useful when the nodes are coming and going. We have these entries which are short-lived, maybe 60 seconds or 2 minutes or 5 minutes. Probably it takes a few minutes to move a host from to disconnect it from one interface in a switch to another interface in a switch. So probably you will probably have these entries good for 2 minutes. And after those 2 minutes these entries will be updated again. During the time when these entries are gone, you will be flooding. And this is flooding which actually allows you to do the learning process. So there is no need to compute the routing state beforehand and use the flood for initial deliveries of the frames and packets, and then learn the location based on where the packet comes from, not where it is going to, but based on where the packet is coming from. So this is only for the active host, the forwarding state is needed. Anyone who transmits a packet, the switches will only learn about it. If somebody doesn't transmit, their location will not be learned. Okay, so this is kind of a plug and play. You can disconnect machines from the switch and connect to another switch, and so on and so forth. So this finishes the discussion on the link layer. Link layer is much more than that. It's a very quick and dirty summary of what link layer is about. And yeah, this finishes all the topics in lecture 28, which will be made available on YouTube. The links will be shared with the class.